Finally, Charles Darwin recognizes that if there are differential rates of survival and or reproduction, those individuals with the favorable traits, advantageous traits that help them better survive and or reproduce, they're going to pass those beneficial traits on to the next generation. Over thousands of generations, these favorable traits will accumulate in the population over time. They're going to become more frequent within the population as the population better adapts to its environment. The population changes over time. The population evolves. Consider the blind cave salamanders. So different species of these salamanders are found in caves all over the world, from southeastern Europe to Texas. The ancestors of blind cave salamanders probably looked a lot like this. These are ancestors that live on the surface and have light in their environments. So long ago, a small group of these individuals, or perhaps one pregnant female, splinters off from the population and makes its way deep down into a cave with no light. Now, if you've ever been spelunking and you turn off your headlamp, you cannot see your hand in front of your face. So in total darkness, eyes are absolutely useless. They do nothing to help you survive and or reproduce. And eyes are energetically expensive to maintain, just like wings in birds that live on islands. Thus, a mutation that aborted the development of the salamander's eyes was strongly selected for, and over time gave those individuals without eyes a selective advantage. Eyelessness became more frequent in the population over time until this favorable mutation was fixed and all cave salamanders were born eyeless. But it's not just salamander lineages. There are many species of blind cave fish from all around the world, and then other cave fish that have greatly reduced eyes compared to their surface-dwelling cousins. Now, as you'll learn about in your discussion this week, some of this eyelessness is the result of genetic mutation. Other eyelessness is the result of methylation, which we're not going to get into now, but you'll learn a little bit about with the Mexican blind cavefish. It's a tetra. More on that in your discussion. But my point is, there are blind salamanders in caves, all kinds of species of blind cavefish. There are blind beetles and scorpions and blind spiders, like this cave-dwelling species of a huntsman spider, which is one you may be familiar with. You've seen the surface cousins. And let us not forget about the blind crawfish. So, like I said, in your discussion, you're going to take a deep dive into what are called troglobites. These are species that have adapted to permanently living in caves, and I really hope you enjoy all of these oddities. But my broader point is that natural selection has exerted similar selection pressures on completely different evolutionary lineages that have colonized these subterranean environments. And favorable traits like the loss of functioning eyes or the loss of pigmentation in the skin, or in this case, the exoskeleton, those advantageous traits have accumulated in the populations over time, becoming fixed in a myriad of different lineages. As the famed evolutionary biologist Richard Dawkins puts it, mutation is random, but natural selection is the very opposite of random, as the loss of eyes has occurred again and again in caves all around the world. Not only do we see natural selection following predictable patterns in caves, but also on planet Earth's evolutionary laboratories, as I like to call them, islands. Remember the flightless cormorants on the Galapagos Islands that we discussed earlier? Well, this is the kakapo. This is a flightless nocturnal parrot that's native to the island of New Zealand. They live in New Zealand's ancient forests. They're moss green giants weighing up to 8 pounds. They evolved in splendid isolation over millions of years on New Zealand, free from mammalian predators that might have otherwise spelled their doom. And they still might, as mammalian predators have been introduced to New Zealand. But the kakapo, over evolutionary time, grew large and heavy. They traded their ancestors' power of flight for a life of leisurely climbing and waddling about the forest floor. And then one more example. This is one of my faves. Do you notice anything different about this rattlesnake? This species no longer has a rattle. So long ago, the ancestor of this species, the red diamond rattlesnake, which lives on the mainland, washed ashore on Santa Catalina Island in the Gulf of California in Mexico. And reminder, why do mainland rattlesnakes rattle their tails? It's a warning to mammalian predators like coyotes and foxes and bobcats, as well as large hooved mammals, like bison that may step on it, but it's saying, back away or I'll strike. Well, like the Galapagos, the island of Santa Catalina is volcanic in origin. So there weren't any mammals other than bats and sea lions that could get there. So the rattle on this island does absolutely nothing to help the rattlesnake survive and reproduce. Thus, nature selected against it. Lastly, I'll end with one more extra credit opportunity. The Module 2 extra credit is all about crazy island oddities, from giant coconut crabs to the Hobbit, a hobbit in quotes, known as Homo florensis. So the presentation, again, extra credit opportunity, is entitled Islands, Planet Earth's Evolutionary Laboratories. You'll find it at the bottom of this module.